We would like now to take a look at the case where, upon trying to substitute in order to find a certain limit, we get a fraction where the numerator is non-zero and the denominator is 0. So an example of that would be the limit as x tends to 1 of x squared plus 2 over x squared minus 1. So if we try to substitute, then on the top, we're getting 3. On the bottom, we're getting 0. And the question is, what is the limit eventually? So before we start discussing how we're going to deal with these limits, let's give a very simple principle. So if we have a function which is positive, and f of x approaches 0 as x approaches a, then the limit as x tends to a of 1 over f of x, so let's think about it before we give the answer here. What could possibly happen? So f of x tends to 0. That means that f of x assumes outputs that are very, very small positive numbers, because we said that f of x is greater than 0. So when you take the reciprocals of really, really small, minuscule positive numbers, then what you find is huge positive numbers. So it's only natural to state here that the limit is going to be positive infinity. On the other hand, if f of x is a negative function, and also f of x approaches 0 as x approaches a, then the limit as x approaches a of 1 over f of x, again, let's think about it. F of x has outputs that are small negative numbers, so the reciprocals are going to be huge negative numbers, and the limit is going to be negative infinity. And we will see that this is a principle that we're going to use. Now, let's go back to the limit that we start up with. So take this limit and try to isolate as much as possible the cause of that 0 on the denominator. That is, we can apply synthetic division. It's actually a very simple factorization, and get that we have x squared plus 2 over x minus 1 times x plus 1. And we could ask, among all of these quantities, which quantity is responsible for the 0 that we see on the denominator? And the answer actually is pretty straightforward. That quantity is x minus 1. Okay, and it's really the critical quantity that we should be looking at here. So here's what we do. We rewrite this as the limit as x tends to 1 of 1 over x minus 1 times x squared plus 2 over x plus 1. And we wonder what we should do from this point. And actually, as x tends to 1, this quantity behaves very, very nicely. It has a very nice limit, right? It's what? It's 3/2. It's a situation where you can just plug in. So now you can start asking what happens with 1 over x minus 1. And 1 over x minus 1 is actually pretty unusual in the sense that we haven't seen such a behavior before. Because think about, as x approaches 1, it could be from the right, in which case x minus 1 is positive, and it's very, very small. So we would have the first behavior that we talked about. And also x approaches 1 also from the left, in which case x minus 1 would be negative, and then we would have the second behavior that we talked about. So exactly because of this dependence on where x approaches from, we're going to split the limit into two limits that we're going to call one-sided limit. So the first one-sided limit, so we will consider the one-sided limits and here's the notation that we're going to use for those limits. Limit as x tends to 1 with a plus here, which means from the right of 1 over x minus 1 times x squared plus 2 over x plus 1. So we're going to call this as x approaches 1 from the right. Okay, and if we want to draw a little picture, here's the number 1. Here's how we're approaching 1 along x's that are larger than 1. And then we will also take the limit as x approaches 1 from the left of 1 over x minus 1 times x squared plus 2 over x plus 1. And this is as x approaches 1 from the left. Okay, so here's the picture right here. And we're asking, why are we making this distinction? Why are we considering these two separate cases? And the answer is because as long as we restrict on one side of 1, we can have a definite sign for the function under consideration, meaning for the function x minus 1. If you're approaching from the right, x minus 1 is positive. If you're approaching from the left, x minus 1 is negative, and we can use these principles. So here's how we're going to finish this. So we're going to say, let's start with the limit as x approaches 1 from the right of 1 over x minus 1 times x squared plus 2 over x plus 1. So what we're going to say here is that x minus 1 is positive, x minus 1 approaches 0, which means that 1 over x minus 1 approaches positive infinity. Okay, so in other words, this part approaches positive infinity. This part, on the other hand, approaches 3/2. And in other words, if you think about it now, you have a product of two quantities. The one quantity approaches really, really large numbers, 1 over x minus 1, and the other quantity approaches just positive numbers close to 3/2. So their limit will be positive infinity. And now let's see what happens with the other limit. So we have the limit as x approaches 1 from the left of 1 over x minus 1 times x squared plus 2 over x plus 1. And now we can argue that x minus 1 is less than 0. X minus 1 approaches also 0, which means that 1 over x minus 1 approaches negative infinity. So now we can say that this approaches negative infinity. This will be approaching 3/2. So if you think about it, you're multiplying huge negative numbers with just positive numbers close to 3/2. So what are you going to get? Huge negative numbers. So this limit is negative infinity. So in particular, the limit as x approaches 1 of x squared plus 2 over x squared minus 1 does not exist. Because the two one-sided limits are different. And actually, it would be quite instructive to try to understand what the function looks like here without claiming that we're constructing the graph in any precise way. Here's the line x equals 1. Okay, it's a vertical line, so this is the line x equals 1. And if you want to understand what the graph does, then what we can say is that on the right, it blows up all the way to infinity. And on the left, it approaches negative infinity. Okay, so the function behaves in a very odd way at the point where the numerator is non-zero and the denominator becomes 0. In fact, we say that this line, the line x equals 1, is a vertical asymptote. Okay. So the other principle that emerges from this whole discussion, and we can use it later, is that the limit as x tends to a of f of x exists if and only if the one-sided limits exist limit as x tends to a from the right of f of x and limit as x tends to a from the left of f of x exist and are equal to each other. Okay, so this is a principle that is very, very useful because sometimes you may have a function that may have a different behavior on the right than from the left. So with all these things together, let's try to look at a different example. And this time, let's start with an example that is already given as a one-sided limit. So as our next example, we're going to do the following. Find the limit as x tends to 2 from the left of x squared minus 7x plus 1 over x cubed plus x minus 10. Okay, so let's see what happens here. Obviously, if we try to plug in, if we attempt to plug in, then we get, what is it on the top? It's 4 minus 14, that's minus 10, plus 1, that's negative 9, over 0. Okay, So that we shouldn't even be writing. So this is not a quantity that is actually valid, makes any sense. We shouldn't even be writing anything that has zero denominator, but that's what we get. So what are we going to do? We have to separate, as we said, the quantity x minus 2. How are we going to separate the quantity x minus 2? Again, we need our best tool so far, which is synthetic division. So if we take 1, 0, 1, negative 10, and 2, we will get 1, 2 here, add it up, 2 here. I'm sorry, it's 4 there. Add it up, and then 10 and 0. Which means that the limit as x tends to 2 from the left of x squared minus 7x plus 1 over x cubed plus x minus 10 can be written as the limit as x tends to 2 from the left of x squared minus 7x plus 1 over x minus 2 times x squared plus 2x plus 5. And now we're going to do this separation that clears things up. And that's pretty much a very simple pattern to follow in such cases. It actually has a very nice argument to it. Sometimes I know that people might want to try to plug in things that are pretty close to the point that we're trying to approach. But this method here is very, very straightforward, very rigorous, and doesn't have you do any of those things. Because right away, you can say what? That this quantity, which is the nice one if you like, as x approaches 2, it approaches what? On the top, you get minus 9. On the bottom, you get 13, right? So it will approach negative 9 over 13. And the truth is that it doesn't really matter that it's negative 9 over 13. What really matters is that it's a negative number, as we're going to see. Why? Because if you look now at x minus 2, what can you say? X minus 2, since you're approaching from the left, is less than 0. X minus 2 approaches 0, which means that 1 over x minus 2 will approach negative infinity. So this quantity here approaches negative infinity. And if you combine them together, on the one hand, you have really huge negative numbers. And on the other hand, you multiply them by moderate negative numbers. Negative times negative gives you positive, and the numbers are still huge. So what you get is positive infinity. Okay, and that's the final answer. So the limit we're looking for is positive infinity. And as a side note to it, we can also claim that the line x equals 2 will be a vertical asymptote for the graph y is equal to x squared minus 7x plus 1 over x cubed plus x minus 10. This one little note that will be useful in many, many such cases. Okay. There is a very interesting vertical asymptote that sometimes people forget, and we should take note of it here, which is for the function ln. So it turns out that the limit as x tends to 0 from the right of ln of x is equal to negative infinity. If you try to draw the logarithmic function, you would see that it looks like this. Okay, so this is y equals ln of x. It tends the x-axis exactly at 1, where because the logarithm of 1, the natural logarithm of 1 is 0. So it turns out that the line x equals 0, what is x equals 0? The y-axis pretty much. So this is the y-axis, is a vertical asymptote for the graph y equals ln of x. Okay, so that's how we treat the situation where when we plug in, we get a non-zero number over 0. And one quick question that we should also address here is, we saw in the two examples that we considered that it seems that that limit had no hope of existing as the limit as x tends to the point under equation from both sides. Is it ever possible that such a limit does exist? And the answer is yes. And maybe the simplest example that one could give is the following one. Take the limit as x tends to 1 of 1 over x minus 1 squared. Okay, if you think about it, x minus 1 squared is positive. X minus 1 squared tends to 0. So by the principle that we explained, 1 over x minus 1 squared tends to positive infinity. So this is positive infinity. What makes this limit different than the limits that we saw before? It's the square for x minus 1 in the denominator. If you look at the other two limits that we did, you will see that the quantity responsible for the 0 in the denominator was raised to power to the first power. Here it's raised to the second power, and that makes it being positive all the time. So in general, for rational functions, whenever you have an asymptote, you will have one of these 4 cases. So you will either have something like what we showed right now. Here the limit exists from, and it's positive infinity because you have the same behavior from both sides. Here's a case where the limit will exist and be negative infinity because it behaves like so from both sides. And then you will have 2 other cases. One case where the limit from the right will be positive infinity and from the left will be negative infinity. And the case where the limit from the right will be negative infinity and the limit from the left will be positive infinity. These are all the possibilities for rational functions when the numerator is non-zero and the denominator is 0. If you look at general functions, you may have many, many more interesting situations. But you know, as usual for cases like this, we're going to stick to rational functions because they provide us with many interesting examples. So to recap, we may have to look at cases where we take the limit at a given point and we need to split our consideration between the one-sided limits, as we did here. Then we can look at a case where from the very beginning, what is given to us is a one-sided limit. And in this case, usually you will find this in the case of rational functions, that the limit does exist. And you have to very carefully consider the limits of the quantities in which you analyze the original quantity and find whether it's positive infinity or negative infinity. Okay, and that's all. Thanks for watching.